The topic for today is actually to take a look, kind of a lower level look at how the radio works, because I think day to day when we design our applications or even just open up our browser and browse around, we don't think about it. And the truth of the matter is our infrastructure, or like layered infrastructure, abstracts all of the complexity of whether we are on a wired connection or a wireless connection, a Wi-Fi connection versus 3G, 2G, or 4G connection, right? All of that is already taken care of. But as it turns out, there are many important implications based on the architecture that you're using or based on the type of connectivity that you have. And specifically, wireless and wired, although they feel the same, right? It's the same TCP packets, just latencies seem to be different, actually dictate different design constraints. And because they're different design constraints, it also means that there are different optimization characteristics for each type of this connection. So if you treat wireless and wired as the same thing, which I think we have a tendency to do in the web community, you will reliably deliver a subpar experience to your users. And hopefully by the end of this presentation, I will convince you that that is indeed the case. And we'll also talk about some of the specifics of what you can do to optimize your sites. So first and foremost, we should start at the beginning, which is to say, why do we care, right? So first of all, when you actually just stop people on the street and ask them about, hey, you have a desktop site and you have a mobile site, what do you expect, right? Just because it's a mobile phone, would you expect the sites to load faster or slower? And the answer is, well, it should load just as fast. Like, what's the problem here, right? It should work just as well. In fact, usually I'm on the go, I'm in a rush, I have my phone out, I want the answer very quickly. So not only should you deliver the experience fast, but you should be even faster than usual. Then you ask that same group of people and you say, like, great, so you've been using this mobile web thing for a while, how's it working out? And it turns out that more than half of them say, well, it's more than half the time it's actually not a very good experience. And the number one reason for this is actually slow load times on these pages. And worst of all, I guess, kind of the bottom line reason for why we care about this as developers is that once a user has this bad experience with a mobile site, they just leave. A lot of them just go somewhere else, right? So it's like, great, I tried your shop, it didn't work, and as we heard at the keynote, I'll just go to Amazon.com because they seem to have figured this thing out. So today we're going to talk about Radio Performance 101, and specifically we're going to compare Wi-Fi and 4G architecture. And we'll touch very briefly on Wi-Fi just for the sake of having a kind of reference points to compare the different wireless technologies, because I think once you put them side by side, it gives you a lot of context for why these things are different and why we should care about it. And then kind of throughout the whole presentation, we'll look at specific performance tips and optimization techniques that you can apply on your own and for your own apps. And I'll leave the last part to you, which is to go back and actually fix some of these things. So kind of, if you work down the stack, right, of all the different layers that are involved in rendering a page, we have many different things that we care about. So at this conference, you're going to hear a lot about things like minifying, CSS and JavaScript optimizing images, domain sharding, how do you optimize GPU performance, CSS performance. Like, there's a lot of different components that have to go into this, and that's kind of where we concentrate on, right? Like, there's a few talks at the event where we talk about optimizing TCP and TLS. But we're going to go actually one level deeper. We'll skip over all of kind of that top level stuff, and we'll focus on the physical connectivity, and specifically on the radio part, which is Wi-Fi versus 3G and 4G. So it's not that the top level parts are not important. They absolutely are important. But it turns out that depending on which of these wireless technologies you're on, they also dictate how or in which order you should optimize your other characteristics. So let's start with Wi-Fi, because it's kind of it's a simpler case. And the thing you need to know about Wi-Fi is the standard was started to get originally developed in the early 90s, and really it saw early success in the late 90s. So 1999 was when the 802.11b standard came out, which is the 11 megabits per second, and that's where it really took off, right? And Wi-Fi is literally an extension to the wireless LAN, right? So it's that plug that you have in your computer. We just added a wireless extension. We took the same protocol stack and added a new medium, which is the wireless communication. And the thing that's interesting about Wi-Fi is it uses a very simple communication model. Let's say so let's say we have a shared communication medium, which is the airwaves, right? And now the question is, how do we actually agree on when everybody talks, right? Because if you have dedicated wires to everybody, then we can just take that wire and talk to an individual person, but with a shared spectrum, we need to somehow figure out how this thing works. And Wi-Fi takes a very hands-off and simple approach, which is the kind of thing that you would have at a party, which is to say, hey, nobody's talking, I need to talk, so I'm going to start talking, right? And everything's good. And if somebody else starts talking in the meantime, then we have a collision, both of us kind of shut up, and then we gauge as to when the next person starts talking. So Wi-Fi does this by simply using this very simple algorithm here, which is anybody talking? No, I'll begin transmission. If there's a collision, then both of us stop. We wait for a random period of time, or an interval of time, and then we start talking. And hopefully that random interval of time is long enough such that we don't end up colliding again, right? And that's all it takes, really. That's Wi-Fi in a nutshell. And the thing is, you can actually prove that in order for a Wi-Fi network to work well, as in to have fairly good transmission rate and good utilization, the network actually needs to be fairly, there can be a lot of activity on the network, right? So the channel load, or the amount of activity on the network, needs to be about below 10%. And I think all of us have experienced cases where we're in a big room at a big conference and Wi-Fi is just not operating all that well, right? So in part, this is why. Because all of us are trying to compete for the same spectrum. There is nobody in there to moderate how the resource assignment is getting scheduled. So we all just talk over each other, right? So if you've ever lost your voice at a party because it's just so loud because everybody's speaking, that's exactly what's happening, except at the Wi-Fi layer. So, if we dig a little bit deeper, we can actually see that Wi-Fi does something smart, which is, we have this, let's say, 60 megahertz of spectrum. We actually separate it into different channels. So if you've ever dug into your wireless router and you've seen channels like 1, 5, and 11, or one of those things, that's what's happening. We're partitioning the channels into 3, and we're saying, look, we can transmit up to kind of 3 parallel streams at once, right? So those guys are not interfering with each other. And the top diagram looks really nice, except that in practice, I took this screenshot just at my house. Wi-Fi has become a victim of its own success. There's so many Wi-Fi access points now that they're all overlapping with each other. And in this case, I had about 16 different wireless access points, all trying to communicate over 3 channels, right? So this is my own router, my neighbor's routers, and all the rest. And we're all competing for the same spectrum. So if I'm on channel, let's say 5, I'm right there in the middle, there's another 5 networks, and one of my neighbors decides to start streaming HD Netflix video, guess what? He's just affected my bandwidth throughput as well. It doesn't matter what my Comcast or whatever bandwidth is, because if I'm going over the Wi-Fi channel, I'm bottlenecked on my due to my neighbor. So tons and tons of overlapping networks, and that has become a problem for Wi-Fi. So here's an example. I ran this test just because I'm a geek and I care about performance and latency. I put my router about 10 feet away from me, right? I have my laptop and I have my router about 10 feet away, and I gathered data for just a simple ping from my laptop to my router. Right, so this is like 15 feet over Wi-Fi, and this is data for over 3 hours on a Saturday night. So this is the time of day that you would see a lot of traffic for things like video streaming and all the rest. And what you see here is that at about 90th percentile, the latency was about 16 milliseconds in the best case, but it was as high as 50 milliseconds. Right, so this is 15 feet. For a packet to travel, 50 milliseconds. Just to put that into perspective, that's about the same amount of time that it takes for a packet to travel from the East Coast to the West Coast. Except here I'm going 15 feet over Wi-Fi, right? So what did I do? Well, this is the 2.4 gigahertz band. I scanned the 5 gigahertz band, and it turns out there's not a lot of people using the 5 gigahertz band right now. So I went out and bought myself a 5 gigahertz router, and check this out. My median time for the first hop is now below 1 millisecond, and my 95th percentile is below 2 milliseconds, right? So there's a huge drop in the median, which of course is a nice win, but even more importantly, we're eliminating these very long tails, right? Which is incredibly important for having a consistent experience and delivering good performance. So some takeaways so far, right? So Wi-Fi provides no guarantees about bandwidth assignment. Somebody comes on, starts streaming video, that's it, right? Or it's not just video; it's any large download, for that matter. And you can't really predict this anyway. So the only thing you can do is adapt, right? So which is why we have things like adaptive bitrate streaming for video, where we stream you 5 or 10 second chunks of video, and we say, hey, how did that go, right? Like, did you manage to download everything? Because if not, we'll downgrade you to a lower experience, and we'll stream you the next chunk, and vice versa. So the server needs to be smart about doing this, right? It's a cooperation between the client and the server, because the server needs to encode the video in many different bit rates, and the client needs to be smart enough to choose the right one. So if you're using, for example, YouTube, that's what we'll do. But if you just drop a file on your static, Nginx server or an Apache server, there's no smarts there. So definitely something you should take into account. Similarly, there's no guarantees on latency or network jitter. So you saw those long tails that I showed you, right, where a 15-foot ping to my router was taking over 100 milliseconds. There's nothing you can do about that, unfortunately. That is just one of the properties of Wi-Fi. It's very simple. It works well in constrained environments, but it doesn't really scale at large deployments. So now let's switch gears and compare this and contrast this against 2G, 3G, and 4G networks. So first of all, these networks were developed with a different set of constraints, right? So Wi-Fi was developed as an extension to your wireless LAN. So we wanted to have this as a capability for your desktop device, for your laptop. Think back to when Wi-Fi was developed. We didn't have phones, with Wi-Fi connectivity. We didn't even really have data plans on phones at that point. So it was never optimized for mobile. Whereas mobile networks are, optimized for mobile. So first of all, we want to deliver stable performance and scalability across the entire network, right? We have a stadium of people. We have 10,000 people in a very small cell, constrained environment. And despite the fact that everybody wants to transmit their favorite photo of, their team playing down below, we need to be able to provide some consistent level of service. That may not be very good. It may be a low bit rate, but we still need to make sure that we can get a 911 call through or something like that, right? So maybe we can ratchet down the bandwidth throughput and the latency spikes, but we can still get through. So that's number one. Number two is Wi-Fi is designed for tens of devices. You can certainly deploy it on a larger scale, but with mobile networks, we're talking about much larger cells, much larger geography, and also many more devices to handle. So that's design criteria number one, right? We want to have some controls on this network, some knobs to say, we're going to dial down the bit rate or the bandwidth rather, but we can support more users. The second one is, of course, battery life. And battery life is something that I think as web developers we haven't really thought about to this date, today, but we'll have to in the near future. Because if you look at the native applications, battery life is definitely a very, very important criteria, right? And you see negative reviews on the app stores that say, this thing killed my app, or killed my battery rather, and I installed the app, right? That's not something you hear about for web pages today. But I think you will soon. You'll start hearing about this soon. And the reason this matters is because radio is actually the second most expensive component in your device in terms of energy consumption. The first one is the screen. The second one is the radio. So we want to turn off the radio as soon as possible. We want to transmit the data. We want to turn off the radio because it's very expensive. And the reason for this is in part because it's not just a radio. So if you look at 4G standards, right, we have things like, we'll give you 1 gigabit throughput. It's like, that's amazing. How are you going to do that? It's like, we just have 8 radios transmitting parallel. Simple as that. And as you can imagine, that burns a lot of power, or a lot of energy, I should say. So you put these two things together, and you get something that is known as the radio resource controller. And the resource controller is basically a moderator. So the way this works is, remember the Wi-Fi model where everybody just talks whenever they want to? With the radio resource controller, basically you have a moderator in a room, which is to say, hey, let's say I want to transmit a packet of data. I first talk to the moderator and I say, hey, in this case, the radio resource controller, I would like to start transmitting data. And the moderator looks into its schedule and says, great, I've got these 5 slots open right now. Why don't you go and start transmit in those exact slots, right? And this is the the transmit power that you should use, this is the encoding that you should use, and this is basically the amount of throughput that you're going to get. I get that response back, and then I can start transmitting data according to that schedule. And then later, the moderator will also say, hey, you've done enough, go into the low power state. There are no messages for you, right? So a very different model. And all of this scheduling is done by the radio resource controller. So this gets us to this point of control and user plane latencies in 4G or mobile networks, I should say. So before we can transmit any packet of data, right? Let's say we have our phone, it's been idle, we pull it out of our pocket, we type in google.com, we hit enter. What happens next? Or we hit go. First, the device will wake up and it'll talk to the tower and say, hey, I would like to start transmitting data. The negotiation will happen between the tower and the device, and it'll go back. So that first step is the control plane latency, right? And if you look at the graph, or the table rather, on the bottom here, you see that for 3G networks, this idle to connected latency can be as high as 2.5 seconds. Right? So this is just us negotiating when you can start transmitting data. So it can be, of course, much lower. It can take half a second, or it can take multiple seconds. With newer generation networks like HSPA Plus and LTE, we've really ratcheted this number down into 100 milliseconds, which is a huge, huge win, right? Because this control plane latency has been a huge cost. And then once you have this resource assignment, you can actually start transmitting data. And the user plane latency is basically the latency between a packet being in your mobile device to a packet being available at the nearby radio tower. And with 4G or LTE, you're looking at about 5 milliseconds. So that's that first hop, right? So remember the example that I showed you with my Wi-Fi router being 1 millisecond. In 4G, that's about 5 milliseconds, right? More likely, you're not using LTE, right? There's a lot of, so LTE and 4G are kind of the same, but they're different. There's marketing that got involved. 4G, typically we call HSPA plus 4G, right? So when we say 4G, assume that, and then you prefix that with LTE 4G to get the true 4G. So not only that, but we talked about control plane latency, right? Let's say we have our 4G network. So first, your phone is idle. You go to active. It takes about 100 milliseconds just to activate your phone. Once your device is active, after about 100 milliseconds of inactivity, so let's say you've transmitted a bunch of data, after about 100 milliseconds, it actually goes into a low power state. So the radio is very expensive to operate. So we're going to stop, or we're going to put the radio into sleep mode where it will only wake up periodically and listen for, is there data that I should be listening for? That happens after about 100 milliseconds. And if you want to go back into active state and start transmitting data back again, you once again need to talk to the tower and say, hey, I would like to once again start transmitting data. And that may incur another 50 or 100 milliseconds. Now, let's say we've actually been idle for more than 100 milliseconds. At this point, your radio will actually be taken into a long sleep mode, where it'll stay for another 100 milliseconds or so. And then after about 10 seconds, it'll cycle back into the idle mode, right? So the thing to take away here is that, first of all, there's all of these control plane latency costs incurred between the transitions. But also look at the fact that we haven't talked about how much data is being transmitted. And we'll see why that's important in a second, right? Like any byte that you transfer will have to incur this transition. So the first takeaway here, I think, is when we design our applications, there's a lot of complaints about like mobile networks are so unpredictable, the latencies are so high, they're so variable, and it turns out that if you actually take into account this control plane latency, which is something that just doesn't exist in wired networks, you can actually model this behavior, right? Which is, my phone has been idle, I need to start transmitting data. Just assume that you will incur, if you're on a 3G network, up to 2 seconds of delay before the first packet even leaves your phone, right? So if you take that into account, you can actually architect your UIs and application to take this into account. And of course, it's not just a simple matter of transmitting a single packet of data, right? Our pages are a lot more complicated than that. First of all, before we even get to all the different resources, we have to go through all the steps of doing things like a DNS lookup, a socket connection, sending the actual HTTP request, fetching the data. And if you just add up the latencies associated with this, right? So I'm picking some numbers here, which is to say, let's assume an average of 200 millisecond RTT for a 4G network, which is a fairly reasonable number. If you add up just the costs of the latency costs, you will see that it'll take anywhere between 600 milliseconds to 3.5 seconds to send one packet back and forth, right? Which is huge. So if you've ever wondered why does this page take 3.5 seconds to render, and then you take into account the actual latency, it's actually kind of a miracle that it works at all. Like, it doesn't take 30 seconds, right? So the good news is with HSPA Plus and LTE, the picture definitely gets better, right? We're consistently under 1 second. In fact, we can get the latencies down into 500 millisecond territory, which is great because our ultimate goal is to deliver all the pages within 1 second or less. That actually means that we can meet this goal most of the time, if we're very careful with how we fetch resources. So the other takeaway here is that we have some pretty good constants that we know our users expect, right? These numbers have held in the early 90s when the first original research on what is a reactive or a good application feels like. It is true today on desktop and mobile. If you want something to feel instant, it needs to respond to the user in 100 milliseconds, right? If you want to keep the user on task, you have to respond within 1 second. Anything over 1 second, you're already kind of losing, the user may be switching context. But you just saw that just sending a packet takes 500 milliseconds to multiple seconds. So that immediately tells you that you can't have any kind of synchronous interactions on your mobile applications. You have to decouple the actual UX from network transfers. You click a button, you have to respond to the user immediately, and then you kick off the transfer in the background, right? You can't wait for the thing to finish to say, great, I fetched that resource. That'll just reliably provide a bad experience for the user. So then the other important thing is these so-called energy tails. So remember that energy, or battery power, I should say, is a design constraint and very important on mobile. And if you think back to our state transitions when we looked at the timeouts, right? So we went from idle to connected to low to a sleep mode, and then back to idle. It basically gives you the step ladder where when we're sleeping and only periodically waking up to sample the actual airwaves, we're consuming less power, right? So we kind of get the step ladder here. But it takes us 10 seconds to go back to idle. So even if you transmit just 1 byte of data, you will have to upgrade the radio to high power state and then cycle back all the way down, right? And it doesn't matter if you're transferring 1 megabyte or 1 byte. So let's do some math. A typical battery today on a mobile device is about 5 watt hours. And don't worry about the specific units here. It's just for sake of example. 5 watt hours is about 18,000 joules of battery capacity. That's what you have on your average phone. Turns out it takes about, this is 4G numbers, LTE numbers, about 10 joules to cycle the radio all the way from idle to connected, and then kind of go through that step ladder back down. Right? So it's just a fixed cost, and this is for a very small transfer. So great, 10 joules. Now, let's say I actually have an app on my phone, which is just sitting there in the background, and every 60 seconds, maybe it's an email check that just pings the server and says, hey, are there any new messages for me? So let's do the math. 60 minutes times 10 joules, that's 600 joules. That will consume about 3% of your battery life per hour. Right? And this is just one application. So now imagine you have several applications sitting in the background, which have non-overlapping intervals, and you're cycling this thing back and forth. Very quickly, after you have a couple of these background apps, you'll find your battery, an hour later, drained by 10% or 12%. And then you make it halfway throughout the day, and your battery is drained, and you're like, what happened? Right? Well, this is what happened. These apps are draining your battery. So each time you have to wake up the device, it's very, very expensive. So another tip in optimization that we should all be doing is, of course, minimizing the number of intermittent transfers on mobile devices, which is to say, you don't want to be doing this kind of dumb polling in the background. And not only that, but you also want to batch your resource transfers, because mobile networks are optimized to transfer large amounts of data quickly, not kind of feed the data bit by bit to your device. So some interesting examples of this stuff that are, that are widespread on the web today are beacons. And there are many examples of this, of real-time analytics, real-time comments, real-time, anything really widget. In this screenshot, it's kind of small, and I don't know if you guys can see it, but this is actually from CNN.com, and they use a real-time analytics solution by Chartbeat, which every 5 seconds just beacons the server saying like, hey, I'm still here. And I'm sure that CNN has a beautiful vanity dashboard somewhere that says like, there's a bajillion real-time users on your site right now, which is excellent, right? It's kind of like, is that useful? I'm not sure. But I can tell you one thing for sure is when you're reading CNN, it's draining your battery like there's no tomorrow, because if you spend 10 minutes reading some article there, or multiple articles, that's 10 minutes of always on radio on your device. So that's definitely an anti-pattern. And earlier today, let's see. You guys saw a demo of the ATT Resource Optimizer tool. Definitely an awesome tool and something that you should check out and play with. You can record a trace of either your actual device or your emulated session if you run it on an Android emulator, and then it exports a TCP dump, and you can basically analyze it or run it across, or against, I should say, a 4G model or a 3G network, and just see how does the radio behave. And I guess most importantly in this context is it'll also try to estimate the amount of energy that trace has consumed. So you can actually load a page and say, like, this page took 400 joules, or this session took 400 joules. Now, is 400 joules good or bad? I can't say, but you can compare it to other sites, or based on your own optimizations that you've applied. So I can't stress this enough, but on mobile devices, it really is all about the battery. So one of the things you want to do is you want to prefetch data. As I said earlier, mobile networks are optimized for bulk data transfer. So what you want to do is, let's say you're building a new site, right? And you have a number of stories that you want to prefetch, or you have a number of stories that you fetch originally, and then there's a bunch of images associated with each. And you know that the user is going to scroll to view most of them. You're actually better off prefetching all of that content early on and then turning off the radio, because that'll decrease the variability and the latency of fetching those things, and it'll also optimize the battery life of the device. Yes, you're potentially incurring more bandwidth there, right? But this is a trade-off that we have to make. And you definitely don't want to be doing polling. You want to be, at the very least, using an adaptive strategy for things like, well, right now the user really wants, this is where your own application logic has to come in. Like, right now the user's checking his email very often, so I'm going to check more frequently. Whereas right now it's middle of the night, maybe I don't need to be polling every 60 seconds. Or applying some similar logic, right? I'm sure you guys can think of other ways. Things like coalescing requests and deferring requests are all smart strategies. And a very good and interesting case study was done by AT&T and Pandora. If you guys just use your favorite search engine and search for Pandora and AT&T and battery, you'll find this case study, and I encourage you all to read it. The context there was that Pandora, if you guys are not familiar, is the music application, right? Where you're streaming music, it's your personalized playlist kind of thing. So, turns out that Pandora was doing a lot of things right. When you clicked play, they would stream the entire MP3 down to your device, right? And then turn off the radio, which is exactly the behavior that you want on a mobile network. But then every 58 seconds or so, they would wake up and beacon back some audience measurement data back to their servers. So things like, how far did the user listen? And did they like it? Did they click? How did they interact with the app? And when they did the analysis, they discovered that these beacons were accounting for 0.2% of the bytes transferred, but 46% of the energy expenditure of that application, just because waking up the radio is so expensive. So Did they have to do that every 60 seconds? Well, no, right? They could do something much smarter, which is on the next play when the radio is already active, just beacon the data back, right? And you could eliminate that entirely. And I think a lot of applications today suffer from this or similar problem. So one of the things you could leverage is things like smart push. So instead of polling the server continuously for is there an update, you can push the update. But even there, you have to be very careful about how you push the updates, because you could very well end up in a situation where you push so many updates that it's actually even less efficient than polling the server. So one really cool feature that I like about on the Google Cloud messaging side is this flag that you can set on the message. So what happens is, instead of pushing a notification directly to the phone, you push it to a Google server, and then it's the Google server responsibility to push the message notification down to the phone, right? And when I send the message to the Google server, I can actually mark it with an additional flag called delay while idle, which does exactly what it sounds like. If the device is idle, the message is kept on the Google server. Once the device becomes active, it is pushed down to the client, right? And then on top of that, you can add things like, by the way, the time to live for this message is 15 seconds, right? Let's say I'm pushing real-time updates of the NBA Finals game, right, to your phone. And great, the team has just scored. I send a message for that. If the message doesn't get delivered within 10 seconds, just drop it on the floor, because it's no longer relevant, right? So these are the kinds of services that both iOS push notifications and Android notifications can provide, and this is the reason why you should investigate using this on your applications, whether that's web or native. And be very careful, as I mentioned earlier, about streaming data. In fact, most of the time you want to avoid streaming data, because that means the radio is constantly on. Instead, you want to prefetch as much as possible, and then use an appropriate strategy. If you're streaming a large video, like a YouTube video, there's nothing you can do. You can't just bulk download the entire 600 megabyte file or whatever that may be. So that's just a trade-off. All right, so let's kind of shift gear and look at a different component of the network, which is the core network. We talked about how the individual device works, but let's kind of take a step back and look at the architecture of the network itself. So first of all, we have the packet gateway, which is there's the outer internet out there, right? And then with the first component that you hit when the packet comes into a mobile carrier is the packet gateway. And think of this thing as just basically your router. It's the same thing as your Wi-Fi router at home. This is that first device within the carrier network. And it's the device that terminates all of the connections, the TCP connections, the UDP connections, so on and so forth. In fact, it's basically a NAT. So the reason this is important is the physical connectivity and the transport connectivity at like TCP or UDP layer are two completely independent concepts. Your radio can be off, meaning it's idle and sitting in my pocket, and the TCP connection is still active, right? I think there's a lot of confusion here. Your phone doesn't need to be on for the TCP connection to be alive. So there's no reason to try and keep the connection alive. In fact, your radio is never really off, which is why I have that star, because when we say the radio is off, all we mean is that the radio is just sleeping for very long intervals of time, and then periodically wakes up and listens to the broadcasts from the radio tower to say like, hey, is there a message for me? Because maybe I should be waking up and doing something. So if you have code like this in your application, please take it out, because you don't need to artificially keep your connections alive. All of that is automatically handled for you by the infrastructure within the carrier network. And in fact, for carriers, the typical timeouts are anywhere between 5 to 30 minutes, right? So most of the time, based on my own experience, is if you have a connection that is timing out in less than 5 minutes, it's probably your own infrastructure, like your own proxy server or something else that is terminating these connections prematurely. So investigate that. Okay, so we went from the packet gateway, we're going to the serving gateway, and we'll see in a second why you need this. So the packet gateway knows nothing about where you are in the network, right? It just takes packets off the external network, it forwards them to the serving gateway. The serving gateway's role and responsibility is to figure out like where should I send send this data, right? With Wi-Fi, it's very simple. You're within a constrained region. With mobile networks, well, you happen to be in Santa Clara right now, then you jump in a car and you're on your way to San Francisco. So I need to be able to track you. So let's take a look at an example here. Outbound data flow. So stay with me here. We wake up the device, we talk to the tower. This is the control plane latency, right? This is the first hop right here. We get our assignment from the radio tower. We send the packets to the tower. The tower sends it to the serving gateway, which routes it to the packet gateway, and then it goes out to the external network. This entire flow right here, you can see some of the numbers from the AT&T network. This is numbers they advertise in their FAQs. The good news is, the numbers are pretty good for 4G networks, 40 to 50 milliseconds. But as you can see, as you move to the right towards earlier generation networks, this flow just within a core network can take several hundred milliseconds, right? And on edge networks, it gets quite bad. The picture is much more interesting and complicated, depending on where you want to be, for inbound data flow. So let's try this out. An external packet arrives from the external network. It goes to the packet gateway. Packet gateway terminates the connection, says, great, I'm going to shuttle it to the serving gateway. The serving gateway gets the packet. It has no idea where you are on the network. It kind of knows that you're maybe in the Bay Area region, right? So first of all, it talks to the MME here. And the MME, or the mobility, I always mix up the name of this guy. Mobility management entity is basically the user database for the entire network. Like, I got the packet. Should I forward it to you? Have you paid your bill? That kind of thing, right? And we also need to track where you are on the network. So the mobility gateway here says, look, I'm also not sure where you are. I think you're in the Santa Clara region, but I'm not sure which exact tower. So what I'm going to do is I'm going to beacon all the towers in this area to just flood the network to say, hey, device number XYZ, there's a message waiting for you, right? So all the towers beacon this data. Your device wakes up periodically. It listens to the broadcast. It catches that and says, hey, I've got a message waiting for me. Let me notify my local tower that I'm registered with you right now. The local tower then talks back to the MME, talks back to the serving gateway, and the serving gateway can then forward the data to the actual tower. So all of this to say, this is actually pretty complicated, right? So if you ever wondered, like, why does it take 200 milliseconds to do all of this routing? This is why, right? The fact that users are mobile and they're continuously migrating from cell to cell is the reason why it takes sometimes so long to route the packet. And that's just for one TCP packet. So, is all of this complexity actually warranted, right? We started with something that was very, very simple. We had the Wi-Fi network, and there was basically nothing involved. Now we have this very complicated architecture. And the answer is yes. It is worth it. Based on some of the tests that we have here, I'll highlight a couple of things. So we have our throughput. So you can see that the throughput compared to Wi-Fi for LTE networks is actually much better. But perhaps more importantly, if you look at the round trip times, right? So it's this block right here. The round trip times compared to Wi-Fi, the median is a little bit higher. But more importantly, is that the jitter is much lower, right? So we don't have this long tail which you see in the Wi-Fi and that you saw earlier in the example that I showed you in my own kind of home environment. Because we control how everything gets scheduled, we can deliver a much more reliable experience, right? There's less variance in the packet delivery. So we're getting good throughput, and we're getting good RTT performance. So that's LTE, and that's the good news. The somewhat bad news is that you can't just count on 4G fixing all things. I mean, it's certainly true that LTE makes mobile performance much, much better. But if you actually look at the trends in the industry, you'll discover that we're going to have our existing 3G and HSPA networks for the next decade. Not for the next couple of years, but they're going to be around for the next decade. Really, worldwide, LTE will start to take over in like 2020s. So the good news is, within the United States and Canada specifically, there's a very good LTE adoption that is way ahead of the curve for the rest of the world. But broadly speaking, you have to assume that there'll be a mix of networks, 3G networks, 3.5, 3.75, and 4G networks that we'll have to work with. So it is a multi-generation future, and you have to plan for this. You can't just design your application for 4G for the optimal case. Even if you have your latest LTE data plan, in this area, you'll find that your device is continuously migrating between LTE, sometimes falling down to even edge, and then sometimes going to maybe HSPA. So bandwidth and latency are variable, connectivity is intermittent, so make sure you do have an offline mode and you plan for this kind of thing. And maybe a little bit of a side point, but this is another big problem that we're discovering with a lot of mobile applications, is some applications don't plan for offline, right? You happen to be standing in this room right now, there's no reception, and your application is just sitting in the loop trying to fetch some resource from the network. And if you ever had the experience of your phone burning your leg, you know exactly how that feels, right? Because the thing is just stuck on a loop, and it's like, yeah, I'm going to try this now, and there's no fail case in that scenario. So what you want is you want to have some sort of a smart backup strategy where you try once, you fail, you try a little bit later, you fail again, you try once more, and then you stop, right? So make sure you're not that application and burning my leg, because you're getting uninstalled. So that's a little bit about optimizing for mobile networks. I do want to come all the way around and just highlight the fact that obviously application optimizations matter quite a bit. Right, so we talked about the lower levels and how you can optimize for this kind of thing, but there are many things that you can do that are just as important, if not even more important sometimes, which is bytes are expensive, literally for a lot of the mobile users, right? If you're ever roamed, then you know that 1 megabyte can cost you $1 or more when you're roaming, so bytes are expensive. The best request is a request that you don't have to make. Caching data you'll be surprised how many applications do not cache data. They don't provide the right cache headers, or if you're building a native application, they simply don't provide an implementation of a cache for their web view or some other thing, and hence no resources are getting cached. Gzipping and optimizing your images. As you guys know, images are over 60% of the bytes of an average page. So optimizing your images is often one of the best optimizations you can do in order to reduce overall costs of the page. So then finally, shameless plug. As Pat mentioned, I've been writing a book about this stuff, which also talks quite a bit about what the architecture of mobile networks and all the rest. So it's free to check out. You can read it online, and O'Reilly has it at their booth as well. So please check it out, and please provide comments on it as well when you read it. So with that, I think I'm running over time, but I can take some questions, and if not, I'll be outside afterwards. Thank you.